So here's another good example where, right, in preparing this, I was thinking about exactly this, right? This range here, this is 2 orders of magnitude, right? And so what we're plotting is, sorry, this is the maximum speed of these organisms. So some scientist, makes it go as fast as it can. And divided by, because scientists are such good people, so divided by their length, the body length, right? So it's normalized by just that piece. So what this says really, and so we have a constant, and this is 22 orders of magnitude for body mass, right? Which maybe is 7 orders of magnitude for a length scale, right? Because body mass is a length cubed-ish kind of thing. So it makes it, body mass and volume always make it look more impressive, right? Because you're covering many more pieces. So let's say it's 7-ish, but 22 in terms of mass. And then there's some variation here, right? So this is, again, 2 orders of magnitude here that it's kind of floating around in. But, fair enough, a fit for this is flat. It's flat, right? So this says as evolution produces bigger and bigger things, sometimes it goes the other way, but generally as it produces bigger and bigger things, that's going to fit within this sort of corridor of what's possible in terms of speed. And this is only for, right, so this is only for running species and swimming ones, right? So it's a mixture of mammals. We've got a few Struthious birds floating around in here. Ants, again, some graduate student has to time some ants. I guess there was no gambling involved, hopefully. But ethics, we will not gamble. Okay, so, and we get out to an elephant out here. Obviously, I had fun drawing these things. Fish, let me see. So let's get this right. So the magenta ones, which are a little hard to see. So this is the running ones. The green one, so yeah, non-mammals are in green. Okay, non-mammals are in green, so that's our ants and so on. And then we've got a lot of swimming ones. So the swimming ones are back here as well. Okay, 2 human ones. This is the fastest running speed for a human. This is the fastest swimming speed. This is, what is this? It's not, maybe it's not an order of magnitude, but maybe 8, something like that. We're not, water is a hard thing to move through for us. We're very slow. Birds, of course, would create a whole different piece here, and it's not in this one. Okay, so that's an interesting thing, right? So can you figure this out from maybe some sort of back-of-the-envelope derivation? And there's a problem for you in assignment 1. You'll notice it kind of trails off here. And so the big story here was this, right? This paper gets published. This is the big story. We kind of have this thing about scaling here, and it's that this, if you like, they could have plotted as, Vmax, right, as a function of length as well, and put that in there. So, or taken out this length, and you'd see it would go up linearly. Oh, yes.
So you would expect that length and body mass would have a really strong correlation at that scale.
Yeah.
Also, if you're normalizing by velocity and length is strongly correlated to body mass, then wouldn't you expect there to be a flat line?
You could certainly put this over here, and you'd have velocity going as, but just scaling linearly. I mean, that's the other way to do this. This isn't governing the whole thing. I mean, this is an important, this is really what it's getting at. The velocity is there. And there's still a lot of room moving around in here. So that's an important piece. Okay, there's a paper that came, so these are recent papers, that's 2015. Yeah, so make sure you get my attention. I appreciate it. 2017, this is a couple of years later. They actually don't cite that paper. I mean, I know this is what happens in science, but it's funny they didn't quite connect because they have the nice little pictures and stuff as well. Again, maybe, I hope you can see this. Flying, running, and so they're flying as well, running and swimming. So this is now just speed and body mass, right? So this is taking away that funny business. And we have kind of a linear growth, but we have a turnover, right? So for the largest things, and I think, so in a way that was the problem here. You lose this, you don't quite, you see something here, but you don't pick it up as clearly as you do if you just put mass and velocity, right? You keep it pretty simple. All right, so there's a rollover here. So the biggest things, and so I guess we're out here at albatrosses. This is, okay, birds, running things and swimming things, and then these are flying things. So this is this broken out here, and then it's again separated out into birds, arthropods, and mammals. Right, we've got some bats in there. These are running things here. So birds, some birds run, of course. Ostriches are in there. Arthropods and so on. Emus, reptiles, all sorts of running things. So they're kind of all generally, fitting together. There's definitely some separation between the three kinds of movement, or general movement. And then we've got the fishy things, octopuses in there. So there's a whole range in there. Of course, that includes mammals as well. We've got some whales. The whole team is in a lot of different teams represented in the swimming situation. All right, so they all have this rollover, and then there's just this very nice piece of work to figure out why that is, right? So basically, how are we doing? Basically, the story is, let's see if we can get through this. I think that's a porcupine, actually. That's a wolf, elephant, and a mouse. So they're the four sort of emblematic species at different organisms at different scales. And the idea is this is their speed, this is the maximum speed, theoretical speed they could get up to if you just sort of assume this linear thing growing as mass. And of course, a mouse doesn't take very long to get going, right? It just goes, and it's at its maximum speed. Elephant has to wind it up. And the problem with that is it uses up all its energy is just sitting there, right? It runs out of time. It doesn't make it to full speed. So gets to some sort of locomotive speed, but then it runs out. So this is a plot of how long it takes to get up to that speed. And I've got some other calculations for this, I suppose. But the point is they burn up all that power energy that they have. Because we have different energy mechanisms or modalities. You have the stuff that can take you, in 10 seconds as fast as you can, whatever, minutes, 2 minutes, and so on. All right, but they run out of gas, and so as a result, they never get to being as fast as something like a wolf or a big cat, for example. Porcupine speed, I guess, is for elephants. So it's at least by this little schematic thing. All right, so that's well done. It's about the energy system that needs to be used. This is a calculation for it, but they do a good job. Fair enough. That's all good. Okay, I think that's good. So I think, they had an enjoyable literature search of maximum speeds of running, flying, and swimming animals. Escape speed, sprint speed, right. It's one of these things that depends on many other people having done lots of work in the past. One paper per organism.